All set. Good to go.
Okay, it is 1 o'clock and I see there are about 107 people, I think, registered. We've got a jam-packed webinar today, so I'm going to get started, and I assume a few people are still going to continue to log on. My name is Caroline Amio, and I'm going to be your moderator for the day. For my day job, I work as a senior project engineer at the City of Waterloo in Ontario, and for fun, I volunteer as a member on the CUIIC Education and Outreach Committee, and from time to time, I moderate these webinars. Next slide. Oh, okay, sorry, we're at this slide. So today's webinar is practical considerations of using ASCE MOP 145 to facilitate design and construction implementation of closed-fit liners. We've got two excellent presenters today. We have Chris Macy and George Bontis to discuss kind of the design and then the construction side. And this is a really exciting topic, and the practical considerations, I think, is something that we all as engineers and contractors and owners, and it's all, this is a great topic. A little more on the CUIIC Academy. It's and this event, it's been organized by CUIIC, as I said, but also in conjunction with the university, which is basically the University of Alberta, but Anne Benjamin Media helps us to host these. The CUIIC Academy also offers, in addition to these webinars, classes, courses, and other events. And the goal and objective is really to further underground infrastructure educational opportunities across all of Canada. So the webinar series, you're all here today, and maybe some of you have seen this before, but we really, on the committee, we try to find a lot of whatever the pressing topics are related to underground infrastructure sector. And if you go on the CUIIC website, you'll see what we have posted, what we have done, and what we're planning. And if you have any ideas, please reach out to CUIIC. There's information on the webpage there. The goal is really for us as an industry to continue education and work together and identify what these issues are that we want to know more about. And we get speakers, industry leading professionals, and it's free educational webinars to the public, and there's question and answer. So they've been really popular and they're continuing to grow. So thank you for coming today. And like I said, check out the website. You can see previous webinars on YouTube as well. And I talked about some other events. There's a Pipeline Academy coming up in Ontario, March 5th and 6th, still spots to register there. A geotechnical workshop, March 10th in Vancouver. Advanced HDD School in Calgary in May, and a safety seminar in Edmonton in September. And that's 2 days. So also, if you want more, those are some great opportunities. Also need to give a big thank you to our webinar series sponsor, to Ackerman. We really appreciate that. A lot goes into putting on these webinars, and we like to thank our sponsor. So now on to our speakers for the day. Today we have George Bontis. He is a Director of Engineering within Situ Form Technologies Limited. He's worked in the trenchless industry for over 20 years. He's an active in numerous AWWA and NASCO committees as a member or chair, AWWA M28, M81, and numerous standards. He's currently chair of the NASTT Northwest chapter, an improved instructor for the NAST CIPP Good Practices course, and he's actively working on the update of the NASTT Good Practices textbook. So lots of excellent background and experience there. Our other presenter today, who's going to present first, and I'm going to hand it over to Chris here shortly, but first I'm going to I'm just going to praise Chris a little bit here. He has over 45 years of experience in assessment and rehab of sewer and water infrastructure. Extensive trenchless experience with CIPP, over 35 years. So he's really been around since we first started using CIPP in the industry, and so a wealth of knowledge, seeing how it's advanced and grown and where it needs to go. And this third point here, recognizes leading authority on the factors that contribute to pipeline deterioration and mitigation techniques, and understanding how pipes fail. Chris is going to get into that, but it's important understanding how we fix them. So it's all part of the same package. He's had extensive involvement in AWWA, CA, rehab committees, ASCE, NACE, NASTT, NASCO, he's TAC member, ISO, and CUIIC. He's helped out with some other webinars too when we've asked him. Blue Ribbon Panel Peer Review Committee for the ASCE Manual of Practice 145 for the design of closed fit liners for gravity sewers, 2021. And he was inducted into the NASTT No Dig Hall of Fame in 2019. So again, we're really lucky to have two such experienced, excellent presenters today. And on that note, I'm going to hand it over to you, Chris.
Thank you. So we'll talk about MOP 145 today, a little bit about a design of close fit liners. It's difficult to talk about that without some context. So we'll give a little bit of evolution of both global North American close fit liner design. We're going to talk about the MOP, or there's no way to talk about it practically. It is intimidates a lot of people. There's a lot of moving parts, and there's some big equations, and it's important to put it into perspective. A big part of understanding the practical side of it, and it is something that is not addressed in more eloquent or more simplified designs, is imperfections and parameter sensitivity. So understanding how many of these moving parts to use and when to use them is a really critical aspect of how you be practical or how you utilize it and don't get lost in the noise of a lot of work. So we got some tricks for parameter assessment, some stuff that you need to do, or, you know, from a design, and it prevents it's a paradigm shift. It is a much different way of doing trenchless than you need to do. And it doesn't mean that it needs to be the way that you do every job, but we will talk about kind of the rationalization of when you pull this out of your toolbox and when you don't, in the context of what matters. So practical considerations, and there's two things about being practical, and you got two different hats we're wearing today. I'm a designer, but I have clients who are contractors, and as a designer, you work with contractors, and per contractor side, they got to build it, they got to deliver it. And the subtlety of MOP 145 is, like I said, a pretty big paradigm shift in how we deliver, in how, you know, like the role of designer. And it's a much more complex, as George will talk to you from his lenses of how you put on these lenses and look at it from the other side in terms of overviewing what design is. The early evolution of design had a number of things that are critical. We invented CIPP in 1971, but there was really no framework for design until Agrawal and Cooper's work was published in 1984. It's actually a 1983 in situ form and design manual that overlaid the first concept of looking at a Timoshenko buckling model, which we'll talk about, unrestrained buckling, and it was the early design manual. And those in situ form design manuals you see posted there from 83, 84, 86, 88, they morphed into what became ASTM F1216. In discussion with Lynn Osborne, who's a wealth of knowledge, and John Gumbel, one of the things that intrigued me is that literally up until the time of F1216, the concept that we talk about today of fully deteriorated design was not done with a buckling model. In essence, when in situ form first visualized how to do a fully deteriorated design, they looked at it really as just ignoring that a hose pipe was there. And they looked at it as a Spangler deflection model, saying if you limit deflection of the liner, you know, after the hose pipe is gone, because that was kind of a vision, that you could just look at it as a deflection model and back calculate it. From what Lynn told me, because I'd asked him how that evolution occurred, is that it was Reynold Watkins was on the committee with him, and Reynold knew an awful lot about deflection. And Reynold told him that basically there was no way that a deflection model, that Spangler's deflection equation, was ever intended to be back solved for thickness. So they abandoned it. They abandoned it and basically took, at that time, the AWA committee was working on the AWA buckling model, which is really based on Lucier buckling. And that's why in F1216, to this day, we see, you know, a buckling model presented there for fully deteriorated design. One of the concepts that we'll talk about today that is important to understand is that concept is this concept of ignoring the hose pipe is flawed, in that, in essence, the hose pipe doesn't go away. And in the words of a man much wiser than me, John Gumbel, you know, once we put this liner in the pipe, you know, it's fine to sit there and say, ignore it, but they're married, you know, like in essence, it's there. And the hose pipe does have a profound impact on how liners design, and ignoring it, especially when you look at kind of the premise of original design, is not a really valid way to go look at liners if you genuinely want to know the loads on them. So across the ocean, there was similarly WRc design, eventually the ATV out of Germany, and the RERA with Olivier Thibault out of France, which has a profound impact on what we look at in MOP 145. And there were some commonalities, but some subtle differences and significant differences in design approach. The other really critical chunk of early work was the work that in situ form had commissioned to get done to better understand long-term behavior. And that was really the evolution of design, and Goose's work at Louisiana Tech, the first long-term structural behavior of putting into context some meat on design in terms of understanding the time-dependent properties of liners, which is a really critical aspect of work. And that is the framework of knowledge. I still go back to this symposium that was held, and it was enlightening. And part of it was holding a symposium to try and get a handle, you know, over how design was done and the differences around the world. And I was organized at University of Waterloo in 2001. Gumbel was there, just boot from Germany. Olivier was there from France. Ian Moore was there, and Ian Doherty from Canada, Hall in the US. A lot of critical people that fundamentally had a large impact on design. Yeah, I would say if there's kind of a weakness in it, is that we looked at two pipes, in essence, that weren't really beat up that much. You learn a lot when you go and dig deep, but in essence, the first conclusion was that, wow, F1216 and the way these pipes, you know, function is kind of sat right in the middle. And I think if you look at face value, is that 13 circular designs were submitted, and F1216 prior to 2007 kind of sat right in the middle of that. And that was basically the Canadian and American said, one says it's fully deteriorated, one said it was partially deteriorated, and they averaged it out, and it sat kind of in the middle of all of these other analytical models on Earth. The subtle thing that we learned from it when you dug a little deeper was that there was a fundamental difference. And it was I know in a paper that Gumbel had written about just trying to understand, and he directly worked with Agrawal and Cooper, but the Agrawal and Cooper model was based originally on the Timoshenko model, which is an unrestrained buckling model. And it was adjusting that model to accommodate for the fact that the pipe is actually constrained. At the same time period, about 1998, Glock had developed one of the first constrained buckling models. And that constrained buckling model more closely aligns with what a liner really sees. The other thing that's subtle in here is that, and it's not surprising, and again, it was brilliant work that Agrawal and Cooper did, but they never tested a pipe bigger than 10 inches. And they had a limited data set. It was very, very innovative work. There's been a lot of work done on confined buckling. And we know now that a confined buckling model is a better, is a more accurate representation of what we're building. And that's critical. The other thing that became really, really clear is a concept in the original 1980s in situ form, is that in the original models, again, proposed by Agrawal and Cooper, is that they dealt with the fact that these host pipes had imperfections. They had things like hinge cracking in the concrete. They had things like the annular gap and how sensitive. What if we didn't really get a close fit? They had things to deal with the fact that some of the, what happens if we have a flat portion of the liner? And imperfections were very, very much a part of European models, and they were basically largely eliminated from F1216. And imperfections, again, we'll talk about today, are one of the reasons, not that they govern all the time, no question about it, but at least you need the ability to understand when it's not a standard case that you've got some unusual one, and imperfections is a big part of what you can do with MOP 145 you can't do with F1216. The evolution kind of came to a head in an ASCE committee report, the PINS committee in 2007. And that really debated the wisdom of continuing to use a Timoshenko solution versus Glock. And why would we not, advance to a model? The reality that a hinged concrete pipe doesn't disappear. A hinged vitrified clay pipe does not disappear over time. And there's the interaction of that and the subtlety of it when you stop the deterioration process that needs to be factored into design. And then the fact that in a traditional model is that when we design, especially when we use the buckling, the AWA buckling model that was there, what it's really designed to analyze in terms of the stress distribution on the pipe is the initial consolidation, process around the pipe. Well, when we're relining pipes, the initial consolidation process is long gone. And if that pipe's broken, the stress distribution is different. And if the pipe hasn't broken, it's a much different stress distribution. And so we need to understand this, the difference between the initial burial condition of the pipe, if that's what we're analyzing, versus a mature burial condition at lining, and how will that, react with pipes. Because one of the observations of the PINS committee was that the AWA buckling model was in essence too conservative. They made an adjustment in equation 1.3, and it's one of the hardest things I have when we go and teach this stuff, because they made an equation that was technically wrong from a practical perspective, because it's not the load that a liner sees, and it's not that they made it right, they made it less wrong. And from a practical perspective, you can still use that under the right equations, but it's very difficult for me as a practitioner to sit there and take an AWA buckling model and move an equations around so that we know that it is less wrong. But in essence, it's not based on load studies. It's just based on it is an understanding of load cells and stuff, but it's a rough concept to go and teach. It works, and because it works, if you use it in the right application, that's fine. But in the context of knowing it or trying to resolve more higher risk assets, you need to look at things in a little bit more detail. The PINS committee basically said that, some portions of this were just too complicated, or too conservative, because they didn't match the real load on the liner. And that's a critical aspect of what we do. And then the other side of the equation is, wow, this original, thought that there's some pipes that we do that, that have imperfections that this model doesn't work for, we better consider those. So what happens if we don't get a close fit? What's the difference between having a flexible hose pipe, and a rigid hose pipe in the context of the way they break down? What happens if we're lining over a thing and we have an intrusion? What happens when we have flats? Those are all things that should be reflected in the model. And again, many of them were addressed in some manner in the original in situ form design and Agrawal and Cooper's design in the 1980s. if you look at what, is the fundamental difference, and I don't think much of us appreciate this, but in the context, if you look at 1216, is the design theory is the initial consolidation process. So it's looking at a host, the way it looks at a liner in the context of load transfer to the liner is in terms of a direct bury pipe and ignoring the hose pipe. And that is problematic in the context of when we go and look at things. Certainly it works, as I said, for a number of things, as we'll talk about later. But MOP 145 is intended to look at true host pipe soil interaction. So it's looking at interaction with the host pipe, and in the context of a broken host pipe or a flexible host pipe, we have earth transfer. It looks at basically the concept of earth transfer. The parley deterioration design that their design states are fully deteriorated in there versus 3 views of state, the Glock-Thico buckling model, which is the way that we respond to hydrostatic stress. The first interaction with soil, which is more in Thipo's work in ASTE 2017. And then the fact that these things may adjust over time. So in areas where it takes time for the host pipe to interact with the soil and mobilize passive soil resistance, a state 3 to extreme with extreme where pipe stiffness really, really matters, and to examine that change. And then the liner, imperfections in 1216 is a validity where we have a whole list of things that are, I won't say the word common, but they occur. And when they do occur, you need the ability to go and assess them. The other thing I don't think a lot of us think about is that the application is that, again, F1216 was never envisioned to be used on flexible pipes. It is a rigid pipe application for circular and less than 10% ovality, whereas the concepts associated with that, and there is a big difference in terms of what happens to a liner in the context of putting it in a flexible hose pipe versus a rigid hose pipe or a rigid hose pipe that's broken. Those are radically different type of load distributions that occurred to the liner. The constrained versus unconstraining, and the concern about it was not that it was not worth it, but the limitations of Agrawal and Cooper work. And if you go and look at this little plot of Glock's buckling versus work that we've seen, you'll see that, the concern over that versus the original line that was drawn from what would be an Agrawal and Cooper style of buckling is that the solutions were divergent. So at very, very light loads in terms of the load on the liner, it's very, very conservative. It's more conservative than it probably has to be. And on the other side, at extreme loads, it's actually on the opposite side of it. Conservative, it's less conservative than we think it is in the context of things. So that was one of the concerns of the committee, and it's one of the reasons we're looking at a constrained versus an unconstrained buckling model. The non-circular side of this is also another really important aspect of it. And again, I'm guilty, like any other engineer, of using this way beyond what it was ever intended, but we used to use WRc design. If you go back and you pick up Glennie's work, Glennie looked at 2 pipe shapes. He looked at a perfect egg or a perfect ovoid. And he developed an FAE model to go and simulate that and came up with some very, very eloquent equations. And you will notice in none of his equations does it include really the geometry between, is it an arc or is it a straight line? And that's the only question. And not, is it an arc or not? And if you've ever gone to work out in the world there, I work in Detroit and I've worked in Cleveland, and in Detroit, I found a drawing that had over 150 different versions of an egg. And when I went to Cleveland, they had another 150 and they didn't match the ones in Detroit. There is an infinite number of variations of these shapes, and they don't match these shapes exactly. So these were limited to 2. And when Olivier Thipo looked at these in 2000, and then Gumbel and Boot looked at them again in the mid 2000s, the concern they had over just using the old WRC solution is that a couple of things is that a constrained buckling model itself, this upper line, didn't explain what was going on with the liner. And they had come up with a better model that considered all of the things we talked about. It's just that sometimes it was less conservative than a WRC. Sometimes it was more conservative, but the WRC solution was basically divergent from what we would see in true load cell work. So you had to know the range of application at which the WRC was not misleading in the context of it. You can look at these two papers if you go Google them. The Olivier Thibault's work is documented in a 2000 paper, and Gumbel and Boots' work. But basically, the importance of looking at these things in terms of their interaction with the hose pipe, and that really forms the basis of how we look at non-circular design today. So more complex than WRC, but honestly, for a non-circular pipe, I wish I could explain it. There's a lot of reasons for circular pipe to continue to use F1216. It is eloquent. It's tough to look at a non-circular pipe in with the same lenses. It is a more complex shape and has more complex loads on it. In the MOP 145 design procedure, in essence, we have 4 steps that are out there to look at the imperfections. It is a factored design resistance, an LFRD model, and we have a variety of limit states. We have, in essence, we're still looking at flexural modulus and strength, but the reality is that can be applied in many different manners. It can be applied in terms of buckling resistance. It can be applied as a serviceability limit to limit deflection. It can be applied in terms of understanding what happens in terms of the hoop direction, of what happens to a liner. So the limit states are a little bit more robust than we look at in F1216, which looks at buckling, literally buckling and strength, and it looks at strength, as we will see, it looks at strength incorrectly in the context of most of our applications. 3, not 2. So we have the view of in a pure hydrostatic stress in a rigid pipe, the first interaction with soil, which is a state 2, and then basically continued deformation over time, where does the liner have the ability to adapt and develop full passive resistance of the soil? What's the long-term condition? A flexible pipe is a different beast, because if you have a flexible hose pipe, in essence, there is no such thing as partially deteriorated design. You will always have some degree of load transfer because the pipe is already deflected and has mobilized passive soil support. So there's 2 conditions. There is this condition that the hose pipe is, has passive support, and it's a little bit more than hydrostatic stress alone, but it is, in essence, the pipe is already at stable. And then you have an extreme condition, is can it accommodate the long-term adjustment associated with material degradation or subtle changes in the soil environment around the pipe. The other thing that we need to understand in terms of this is for flexible liners. This is for liners that are designed as flexible materials. Basically, they have the ability to deflect over time without cracking, and that means that a spray-on rigid liner doesn't count, like a geopolymer or cementitious liner. A polymeric one that can bend is definitely, follow the theory, but not rigid products. These imperfections are a beast. I wish they were simple. They are actually not overly complex, but the good thing about them is that the more work you do on imperfections is they have to be pretty profound before they really govern design. And some of the examples we'll give you is that they may govern design, but they actually govern design by such a small amount that it's not that big a deal. Some of them do, and they catch you up. And that's kind of the subtle things of these practical observations of doing sensitivity analysis. And it is one of the really important ways that we understand design. So the other thing, again, the reality of imperfections is that when we move into reinforced products, or we move into mechanical properties are much higher, the point at which they intervene is far, far less, in terms of how it dominates things. The other thing that I find impractical or just tough to deal with is that the way that they're defined in the MOP is in terms of an angle that I've never measured in my life, and that, quite frankly, we will never be able to measure. So we can't estimate these parameters by back calculating by other methods. So in the context of a 4-hinge ovality, well, we estimate that all the time. We can visually do that and then back calculate the significance of what that is on the pipe. If you have a camera centered in a circular pipe, You can use a pixel counter and accurately measure deflection. You don't need LiDAR for it. And you will be in the ballpark of what it is, and you can back calculate the equation to solve for it. So it's not, a radical concept in terms of what you need to do. The good thing about the flat side of things in terms of it is that when you do sensitivity analysis, even on an unreinforced fault, it's got to be a whopping big beam before it really dominates. Typically in sensitivity analysis that we've done, it needs to be about a third of the diameter before it governs. And we don't see a lot of flats of that magnitude. So again, some sensitivity analysis to know whether it governs or not. And again, you're never going to visualize what that angle is, but if you appreciate that, if you know you can estimate the length of the flat relative to the diameter, you can back calculate what that angle is and do the math associated with it. So from a visual, identification technique, you need to look at it in practical terms to back calculate the defect. Intrusions are a little different beast because you think about them, they are, when we're looking at buckling, it's already buckled. Okay, we've lined over a surface that is exactly the opposite of how we want it. So intrusions are subtle, and they do need some understanding of their significance. This is a pipe that we looked at in Cleveland. This was an emergency repair, and if you look closely at the video, there's an intruding lateral that they really couldn't take out. So it basically had lined over this and then post-grouted it from the perspective of filling the void. But you'll see this little blip on the inside. And again, in checking that, found that the shape that we had created actually governed design. Not by a lot, but in fact that the design needed to be a little bit more conservative because of the intrusion. So it is a subtle thing that you need to do, and you need to do some sensitivity analysis. Again, the amount that it modified design is probably within the processing allowance that George would have allowed anyways, from a practical perspective, between the thickness we calculate and the thickness that we use in practice to take a piece of CIPP and put it in service and allow for processing. But in essence, it did govern design. And then from a practical perspective, George often sends me pictures like this because this is a rigid concrete pipe with an ugly looking crack in it at the beginning of hinge. And in essence, they were asked to line over this. So we're going to do exactly that. We're going to induce corrosion. And that's a complicated, it's an easy thing to solve mathematically, but it is a little bit more complicated to understand what is that deformed shape going to be. So a little bit of sensitivity analysis is required to understand what impact that has on design. The ideal of what you're looking at is that same little blip on the bottom turned on its side, but analytically within the context of MOP 145, you have the ability to look at it and solve that problem to see if it governs design and to understand how big a blip and how flat it has to be over, sort of what sort of an area, before it would govern design and how conservative you do. But it gives you the ability to look at it, and it is something that with sensitivity analysis, you can exercise good engineering judgment as to how to accommodate it. The annular gap is a big deal in these. And the liner resistance in the annular gap is a problem. One of the enlightening things for me is when I pick up ASTM D5813, it basically tells us that we can allow 2% shrinkage on a liner. And in an 8-inch pipe, that's not that big a deal. But in a 24-inch pipe, a 36-inch pipe, that's a really big deal. And in essence, it will govern design. So from a practical perspective, you need to understand the potential for the impact of a gap on shrinkage. The good news in it is that it's a processing issue. It's not a sizing issue. Liners stretch. Even a reinforced tube has got the ability with the right head on it and good judgment in terms of sizing it. And during the curing process, the process of the resin curing is actually allows or forces the liner to expand outwards towards the wall. It's the process of stopping it from curing. And basically, if you interrupt the curing process before it is completed, and if you cool down too quick, you will induce shrinkage. And that's what causes an annular gap. So from a practical perspective, this is a process control issue. You can control it. And when we get into a reinforced, it's a function of the amount of resin you have in the pipe wall. So in a reinforced tube, we have a lot less to control. from a from a practical perspective, because there's less resin volatilizing, that can shrink at the end of the day or induce that shrinkage. But it needs to be addressed, and in larger pipes, from a practical perspective, up to about 600 mils or 24-inch, I can see whether I got a close fit. You can see the interface of the liner. But for large projects, you need some means to sit there and either do sounding, take some samples, to sit there but the core of it is you need to really, really focus on process control. Make sure that the liner is adequately cured, and then two, make sure that the cool down process isn't just ignored in the context of reinstating that in the context of steam cures and hot water cures. The gap, again, is an area that from a practical perspective, the reason that we focus on it is that or make sure it doesn't fall through the holes at the end of the day, is that relative to our previous view, is it has a greater impact than predicted by Agrawal and Cooper's work, and it's divergent. It's much like the constrained buckling model. And all of the load cell work we have done on gap since then has basically given us, reinforced that a constrained buckling model is a better representation of the process than the original work in terms of trying to modify an unconstrained buckling. Reinforcement, as I said, has a profound impact. One of the things that F1216 does is it limits you from using, greater than 10%, ovality in a pipe. And this is what ovality does in F1216 is it predicts basically on the other side a very, very conservative tube where in fact the increase in buckling is actually linear over that process. We look at the true impact on it. So it basically would yes, you say it just makes me make a thicker liner. Well, it may make me make a liner that is very difficult to cure. And if I make the liner too thick and I can't cure it, I don't get full cure, I have a greater probability of getting an annulus gap. So you want the liner to be structurally robust enough, but you don't want it to be so robust that in essence, you've compromised your ability to get a proper cure on it. And a proper cure is the way that in essence, you minimize the manular gap. And a lot of the sensitivity of this, as I said, as you get into a reinforced product change. I'm not telling you to use a reinforced product, but just understand the subtleties of them in the context of the difference of their impact on imperfections. The last thing I'm going to talk about before giving George a few minutes to talk is the non-circular parameter assessment. The reality is that the MOP wants a radius. They want a real dimension. And that's much different than the work of Glennie and the old model. And most of us scratch our head at that. So certainly, the work we do in preliminary work, there's very few of us that have done LiDAR and sonar, out there in point clouds. It can be done. It's a lot more expensive. So you got to rationalize, what is the sensitivity of understanding that radius before looking at a record drawing or try to understand it. But it is a reality, and in standard, how those pipes are constructed is very important. So concrete pipes, you can typically get away with, without doing this as pre-work, but you certainly will need to verify it in the field. Flexible pipes get to be a little trickier, and I can illustrate that in a moment. If you just go and take a look at this. This was a colleague of mine presented this, and unless you look really, really at the back part of this picture, this looks like a circle to me. And that's, of course, a corrugated steel pipe that is a whopping big arch. And, its record drawings indicated it was a 59 high by 81. That doesn't look like that. That's visually very, very difficult to see in a CCTV camera. And we actually measured it. It was actually 59 by 85 inches wide, just in terms of how it responded or the subtlety of how it is there. So those are important things to understand as we get into flexible pipe. Radius is a big deal. They can be off quite a bit. How accurate? If you don't do sensitivity analysis, you'll never have any sense for radius, but it is important to do sensitivity analysis when you do look at radii, because you'll never have radii to 3 decimal places. You won't find out until you literally get into the construction phase and you're trying to measure it. So understanding the impact of the significant impact of the thickness going down or up, and how accurate you have to do for a particular shape is a good piece of sensitivity analysis to do. The other thing that, again, how do you go out and measure that in the field? And in a circle and an aid, I had to do some digging, and you need to understand what a sagitta is. And I didn't know what a sagitta was until I started doing loss of ground calculations. But if you go out with something as simple as a straight edge that's a fixed length, and it can be anywhere along the radius, if you basically measure the length of that, and you know the length that you measured, and you take yourself and you measure the maximum kind of deviation from the straight line on the radius, you can back calculate the radius with the sagitta and a chord length, basically half the chord length. I will caution you that there's a lot of subtle derivations of this based on whether it's the whole chord length, the half chord length, or how you do it. This is a rather simple way of looking at it. But again, a very practical way to go in and find out what radius in the field to confirm design just by taking a straight edge, plopping it on the wall, and measuring the maximum offset from it. You can have a practical way to understand that. The last thing on a flexible pipe that is a subtle thing is the original work in WRC really didn't look at this. They looked at it as a beam or a curved beam. And one of the subtle things that can happen in a pipe is that we get hinging in an egg shape or in an arch shape in the middle of the arch. And George and I found out this the hard way, is that whether you put the hinge basically in the middle of the arch or literally with this type of cracking, it has a profound impact on thickness design. And that is very significant to sit there and make a decision as a designer as to whether you're dealing with this form of cracking or this form of cracking. Within the MOP 45, you have the ability to adjust it, and it is an important aspect of it. In the context of this, if you're lining it and you're stopping it from deteriorating and there's no cracking there now, the rationalization is that it's not a cracked one. If you don't know or you're afraid, in essence, you would sit there and make the judgment that you want to deal with basically the blister or the imperfection right in the middle of the arch. But it has a profound impact on design. And with that, I'm going to turn it over to George, and he's going to go through some of the challenges as he sees it from a practical perspective of all the crap that a designer says when they say, Mr. Contractor, I'm just offloading design on you. You figure this out.
There we go. I believe I'm live now. Can you hear me, Chris?
Good.
Thanks. So, in addition to the challenges of MOP 145, one of the real challenges in life is coming on after Chris Macy in a presentation. He's very knowledgeable and he gets into a lot of detail. What I wanted to talk about with this slot is how do we, as Chris mentioned, how do we implement this with our own systems, or how is the contractor going to deal with it? At this point, it's a fairly new system. It's got 2 or 3 years that we have under our belts, but not everybody understands it fully. If we look back at at history, when we were working with the WRC to come up with non-circular designs. As Chris mentioned, there were 2 essential shapes that were worked with, and then there were tricks that had to be played to assess arches and other strange shapes. For the arches, we would use a WRC on the bottom, and on the top, we would use a more conventional assessment, something like F1216. And even then, there were issues that came up in the contracting world where not everybody was playing with the same deck. It was very difficult to for the owners, for the contractors and the engineers to make sure you're comparing apples to apples. So one of the things that came up over time was some of the consultants started providing a lot more information, than just the basics as far as the inputs or the parameters that could be specified. And in that regard, we ended up with either curves where you could visually pull the information off, or sometimes we ended up with a set of formulas that would allow us to design for the conditions that the initial designer actually expected. And in some cases, the curves weren't always friendly. So for a given liner, depending on the material that was chosen, you might have two different equations that you would plug into just because of where you were in the relationship between the material and the thickness. We definitely need to look more at the parameters. As Chris mentioned, we found out just recently on that oddball shape that he spoke about that looked like an upside down fat egg. It's actually an arch. And by assessing where the buckling was taking place, it ended up with a 30% increase in liner thickness when you compared the buckling in the vertical as opposed to the horizontal. And that's where you have to be careful with those. We see a lot of changes in the post bid because we don't often have very detailed profiling. Some of the commercial software requires or expects that you have very, very detailed information on where do you actually go with the radii and the important factors that you have to consider. The graphic that you see there comes out of the MOP 145 manual. It's a bit of a beast, but very logical if you follow it all the way through. But you can't skip steps, and you have to understand what it is that you're trying to accomplish. Slip lining sections are a bit more complex because we're not forming directly to the hose pipe like we do with CIPP. And then something that always comes up in those situations is the grouting pressures, making sure you don't damage the installed liner prior to while you're grouting it. And one of the things Chris showed the graph comparing WRC to the new method and where we actually are with the thickness calculations. We thought that WRC was very conservative, and it turns out in some cases it's not. And in this particular situation with this upside down egg again, it was the shape that actually caused a lot of concern, because WRC, again, you're working with egg shapes or verticals, and that made a big difference to us. Next slide, page down. Oops. Trying to advance the slide. There we go. There we go. Sorry. With that roadmap again to the left, you can see a list of equations that have to be solved. There are over 40 equations that are solved, and this is in proprietary software. You don't always see this in some of the commercial software. I'm sure that most practitioners that are going to be getting into it have developed or are working on these types of programs where they can actually understand and see what's going on, as opposed to the black box approach. These next slides that you see here on this slide, the items that come up are actually the equations that are being calculated. And again, there are 40 plus of them. Wherever you see a curve or a graphic, typically it's indicative of an iterative solution. So you can see there's a lot of work that has to be done. It's not something that I don't think you'd ever want to do freehand or by hand without having a program to work with. These are the rating curves that we discussed earlier. The top one is for varying flexural modulus. The bottom one is for the flexural strength. And so depending on the material properties at the bottom of the curve, at the bottom on the x-axis, you can go up and you can pull off the thickness that you should be aiming for. And it's a combination. You have to check both the flexural strength and the flexural modulus, obviously. And you pick the one that gives you the thickest liner. As you can see, these aren't straight lines, so there can be some variations as you change. The beauty of it, though, is that it allows any contractor to come in and bid on the same basis as the second contractor or whoever, because you can put in the material properties that you're comfortable with or that your product actually uses. When we end up with these curves, it gives us that ability. Now, in the contract, as I mentioned before, that we don't always have the best information on the cross-section. So in the contract mechanism, it's a real plus if we actually have a contingency or a way to count for the changes in conditions and imperfections. The example that Chris showed you where it looked like there was a blob of cement on the side of the pipe, that is actually what we believe it was. It's a 600 millimeter pipe, not able to get in and check. But there was a spray on cementitious coating, and it folded in that one particular case. Can you line that with a standard, F1216 design? Probably not. A similar case was in an egg-shaped pipe where we ended up with a large protrusion because of a repair, and it was one of those things where you could do man entry. Nobody wanted to get in there because you didn't know what was behind it. Did you have a solid concrete behind it, or was it not? This again had to be designed with the 145, and we were able to come up with a process that made sense to both the consultant and the owner, as well as our guys. Where is this appropriate? It's seeing a lot of traction with the CIPP lining, slip lining with plastic and glass fiber, reinforced pipe with in those cases, again, you have to grout the annulus, and the fold and form thermoplastics. I think the biggest application for it's is going to be obviously in the non-circular pipes. However, as Chris mentioned, when you start getting into the larger diameter pipes, is it 450 millimeter or 900 millimeter, and where does that gap start to influence the design, the annular gap?
Hello, is this George?
Sorry. Somebody called me that I couldn't get rid of. I don't know if you heard that. Sorry. So we get into pipes with the larger deflections. We have 1216 is limited when you get up to over 10% ovality. When we start getting those larger deflections or imperfections that I mentioned, F1216, it's still a good tool. We need to understand where's the envelope for it, and where do we start transitioning, and we need to be able to communicate those situations clearly. And Chris, I guess you're back up.
Yeah. Just to reiterate, it's an evolution of the design process, and one of the things that's real is that it certainly is a more accurate view, sometimes thicker, sometimes thinner. But it is more reflective. And that doesn't mean just because it's more technically correct. George articulated, and I would reiterate, there's a lot of moving parts. So it's important to articulate this in a manner that George said, in a manner that can be bid, that's fair, that in essence people understand it. And that means thinking a little bit outside the box. it's, your parameter selection, understanding sensitivity and precision is a really, really critical part. Certainly in the context of we have two questions in here I can see, and one of them, is CUIIC. And yes, CUIIC is a verified piece of software. It's not the only piece of software, but it is a verified piece of software that Olivier works on with Jordanka, and is a very reliable, tool in the context of it. It does look at one case at a time, so doing sensitivity analysis of it requires quite a bit of work, and certainly that's the type of stuff that George and I are working on, is ways that we can do more sensitivity analysis with it, because it's not, you can see then radius is a non-circular pipe. Understanding kind of how accurate you have to be is really, really, is important. The other one that we touched on, and I'll talk about, is very, very important, is that MOP 145 and ASTM F1216 are for flexible materials. A spray-on mortar, a spray-on geopolymer is not checked in either F1216 or MOP 145. Those are rigid materials. They need to be assessed for a rigid material. It needs to be assessed for crack control. It needs to be assessed for thrust. It needs to be assessed for shear. A million things that a flexible product will not see. And that's not saying that one's good or one's bad. It's just that it's not the technical corrects. We wouldn't design a piece of concrete the way we design a piece of PVC pipe. You wouldn't think of it. So understand these things in the context of rigid or semi-rigid materials versus flexible materials. If they're flexible, MOP 145 as well as F1216 has a place. In the context of rigid to semi-rigid materials, it's not the right technical approach in the context of the way to look at it. So with that, I think we've summed up. Like I said, it's a lot to do, but it is certainly, from a practical perspective, it's really, really important to understand the change we talk about in the context of doing design or this equitable distribution design, being a little innovative in terms of how you put your contracts out to reflect that distribution of risk, and to make things fair and equitable from the perspective of understanding a way to get complex jobs done. And with that, with 3 minutes left, I will, unless there's any more questions, I'll turn it back to Carol and see if there's any more questions out there.
Thanks a lot, Chris and George, and thank you to CUIIC members. Just up on the screen there are a bunch of questions that have come in, so I'm just going to go quick here. I'm just going to start off by saying I do believe that we will, CUIIC will post them after if we don't get to all of them. So I'll just put that out there. We'll start with just how they came in. Are you familiar with the program? Oh, Clint, I think you spoke to this one, Chris, that automates.
Yeah, the first two, the question 2 and question 3 about flexible liners, we answered. And question 4 is a kind of like question 2. It's out there, and I'm not aware of commercially available. I am aware of a lot of us who have been working on tools. Clint is the most prominent one that I'm aware of as a commercially available one, but in essence, I have verified that with enough stubbornness and enough work, the MOP 145, you can sit there and develop a tool. It's not for the faint of heart, so it is stuff that we have to share in dissemination of knowledge, but it certainly can be done. Go ahead. You pick what else we're going to address.
What are the typical controlling design parameters in odd shape situations? This is from Chad in the city of Calgary.
It is important to check, the subtlety that we talked about is that for many of the imperfections, like a flat, in essence, the flat has to be quite pronounced before it'll ever govern. The reason that we focused on intrusions is that defects that, cause the liner to have to perform in a manner totally inconsistent with how it's designed, like an intrusion, is an odd situation that requires, again, looking at the structure of the MOC, making sure you assess the parameter. For the other ones that, that are listed in there, and again, the third one that we talked about in non-circular ones is basically whether the defect occurs, literally on in the middle of the beam, or basically if it's hinging different. So those are kind of the big things, and the reason that we highlighted them today is they're the things that can have a profound impact on design inadvertently, and those are critical defects to check from the imperfection side.
I guess I'm going to go to the next question, and this is from Alexandra Bruchet at CIMA Plus. Where can one get in-depth training at designing with MOP 145 or designing liners in general?
Well, the training that we offer through NASTT will touch upon that. I don't know if it's going to touch upon it in enough detail, but we spend a good quarter of the day on design, but a large part of that is design and implementation, so it's verification. I know through CUIIC, it's something that if there's an interest expressed, I can't imagine that CUIIC's not going to say, let's just fatten this up and talk about design in more detail. So in the context of reaching out, those are the two primary sources. The inspection side of it, and we've touched upon it at NASCO, is more on the inspection side and critical things, but we haven't put modules out yet on the design side. I know the new CIPP course from NASTT addresses MOP 145. Whether we press in enough detail for you is another story, but because there's a lot to cover. But in essence, that's kind of the mechanisms I'm aware of to go out and get some training.
Okay,
Chris, one thing on top of that,
yeah,
you know, there are these training sessions available, but from what I've seen and what I've experienced, the best way that you're gonna learn is just repetitive use. It's not gonna happen in one course. You're not gonna get it. You're gonna have to go out and mess with the software that you have and learn from your mistakes.
Okay, so good question 8 there, if you'd like that one addressed before.
Yeah, let's do number 8. We're a little over, but I think we can get to it quickly. Yeah. Pre-installation, how can you estimate the gap between the liner and host? Would designs assume some nominal amount of gap based on shape, or that controls that will make it a tight fit?
That's a very good question. So that is one of the strengths of the MOP. And I can tell you from a job that we're offering some support on right now that is about 35,000 feet of 84-inch through 120-inch diameter liner, that is exactly the question. So from a practical design, we're doing some sensitivity analysis to ask the question a different way, is how big does the gap have to be before I can find it? You know what I mean? From a practical perspective. And we're looking at the sensitivity of design to make sure that we accommodate a certain amount of shrinkage beyond the nominal amount. And that, from a practical perspective, is going to be a number that's certainly, less than half an inch, but it's not going to be 1 millimeter. It's going to be a smaller number. So from a practical perspective, you need to iterate to see at what point it has a profound impact on design, and you can do that again within the both Clint and the calculators that we work with. That is something that you can do iteratively in design to get a sense for how big a gap are you looking for, and to put the controls in place. And as I said, the primary controls that you really need to address are on the process side. So the normal spec that we write to make sure that the liner gets the mechanical properties are the way that you mitigate the gap. So by beating someone with a stick and making sure that they fully cure the liner, that they keep the head on long enough that they don't walk away from the curing process before it's complete, that is the best way that you minimize the gap. And again, in a pipe up to about 24 inches and kind of bordering on that, you can visually see a close fit. Beyond that, you're going to have to do something, as radical as sounding the pipe, or literally doing in a big enough job, a couple of coupons and repair the liner, which I know is a heinous thing to do, but it is in a big installation. You need to give some thought to how you can do that. from a contractual perspective. Hopefully that answers your question.
Okay, there was another question about the gap. Just maybe because we are at 12:04, I don't know if Chelsea's on there. How much are we allowed to go over? Anyway, we can keep going till someone kicks us off. I think you guys can see the questions too, right? And I think you just answered this one about regarding the annual gap in MOP. Why is the maximum recommended equal to 0.04 inches?
It's a good question, and it's not one I particularly have an answer to. It's one that it's the size of meeting it. It'll probably come out for clarification, but we routinely analyze basically gaps larger than 0.04. It doesn't mean you strive to do it, but it's a point at which the annulus will not govern. Done sensitivity analysis on liners, and for most installations, you can get a gap bigger than 0.04, and structurally it doesn't impact it. There's some good work that Texas A&M did. So I don't have a definitive answer because I reviewed MOP, but from a practical perspective, the review of material shrinkage characteristics, again, in smaller liners, suggested that, that was a reasonable objective, based on the shrinkage of a resin, looking at how far 0.5% would go. We certainly have designed them and looked at them and verified them to be less than that, but I don't have a definitive answer as to why the recommended is other than at 0.04, you've got a clean constrained buckling one with literally, where Glock's original work, where the THPO block modification that we use, in essence, is entirely accurate, not compromised by that. But you can work with greater ones. As I said, if you go look up the text, I think it's a Texas A&M that looked at increasing at what point you lose all of the benefits of constrained buckling, and it's a bigger number than 0.04. So.
Well, and shouldn't that be adjusted depending on the diameter of the pipe you're dealing with?
There's no question part of the modification or the commentary that you'll see correction on a MOP 145 will address exactly that, is the importance of checking that in larger diameters. And it's the reason I put it in the presentation today, is it becomes very important at about 36 inch and up to start and have means, one, to analyze it in design as being a bigger gap, and two, from a practical perspective, have means to verify that in the construction phase.
Okay. Hopefully that answered your question. I just see the next one. This is City of Portland again. I second the design to see a CUIIC presentation on the design, walking through the calcs for specific situations. I'll bring that back to the Education Committee, and I think we had a great turnout, lots of great questions, and clearly there's more to understand here. Number 15, how important are soil geotechnical parameters for inclusion in the procurement package for design parameters? Again,
from a practical perspective, it doesn't differ a lot than the way we do F1216 design. The most important thing that you're trying to highlight is there very, very soft soils. So in a medium stiffness material or higher, which is kind of the realm of 700 to 1,000 psi, and I apologize, I'm a Canadian, I'm talking in psi to another Canadian, but about 6.8 MPa. If you're in the type of soils that are that, you don't need to sit there and rationalize how much higher than that, because you're, as a designer, you're not going to look for a lot. You're looking for the onset. I'm concerned when I go work in areas where the soils log tells me we're in very, very soft materials, where basically the modulus of soil reaction is markedly less than 500 psi. So you don't need to understand them. And I know if you're from Calgary, you're asking that, you have a good understanding of regional soils and whether you have areas that are fly like that. I know as a Canadian, if I'm in Richmond, BC, boy, I need to understand the other end of that equation. I know in areas that we go look at where you have to flag it, but the vast majority of things, once you're above that threshold, you need to develop passive support, not passive support that, there's extraordinary or, extraordinarily high values. Hopefully that would be value. That answers your question.
Just because we have one more minute, I got the message. You can go to 2:10. It's still 2:10. We got a minute.
Yeah.
Okay. So is there an update on expected performance of flexible liners?
I wish I understood what the question was. You mean life? If it's life, there certainly is. If you keep the stress levels low and you follow all the type testing, we've done quite a bit of performance of this with CIPP. Is you can certainly design CIPP to have design lives much longer than 50 years. If you don't follow these practices and you ignore them, you can cause them to fail very, very quickly and look at very bad installations. But with the minimum level of effort of following good practices, you can get hundreds of years out of a flexible liner.
Okay, I think that's all we have time for, and I think we kind of got through a lot of them, most of them, and hopefully we answered your question. If not, I guess there's still opportunity for follow-up maybe. And
if we
yes,
get these, we just make sure they're answered at the end of the day. So
yeah, CUIIC should provide the slides and the webinar recording as well. And I think to any questions that we didn't get to. I think we did get to all of them though. Yeah. Okay, well, thanks a lot, Chris and George. I think that was really useful and timely discussion, it seems like, for a lot. So yeah, I'm going to bring that back about maybe considering looking at doing another, maybe it's a more than a webinar on this topic for people that want more detail. It's really hard to jam that all in 45 minutes, understanding all the elements. So, all right. Well, thanks a lot. And thank you everyone for coming. Have a great day.
Thank you very kindly.
Yep. Okay.
Thanks a lot. Bye-bye.
Bye.